All right. So let's take a look at the theory behind what we just did in demo there. So like I say, you got the procedure linkage table and the global offset table. Those are tables that include addresses that ultimately go to the library. So we overwrote the exit address to point to our injected shellcode and ran it. So when the developer thought they were executing exit, they were in fact going to execute our code instead. That's how we took over the box. So you write to the global offset table and write to it 4 times to get all 4 bytes. And then we inserted dummy shellcode that consisted of 100 NOPs and 250 breaks just to make a placeholder so we could see that on the stack and figure out where the NOPs were, choose an address in the middle of the NOPs, and then the dummy shellcode will run and hit the CCs. It'll hit a trace breakpoint trap, which is what happens when it works. Now, we didn't do it, but to test for bad characters, you just take where you were going to put in the shellcode and you just insert all the characters, 1 through 256. And then you'll see, when you look on the stack, that it only inserted characters up to a breaking character and then stopped. So if you leave a space in, it'll stop there. If you leave a carriage return in, it'll stop there, and a tab, and so on. So that's how you can discover that these characters are all forbidden, which is kind of obvious anyway, if you just know how C reads. C reads up to the first white space, and these are the white space characters. So any one of these will cause it to break the incoming string. All right. And all right. So then you generate shellcode using Metasploit. It writes the Python for you. You stick the Python in the script, and you can get in. So now there was a discussion here of countermeasures I wanted to get to, and somehow I failed to. Right, here we are. There we are. So this %n format string is the fundamental weakness. So if the user can control the format string, which they shouldn't be able to, but your developer might make a mistake and forget to put in a format string somewhere, that will do it, then all the printf commands are vulnerable to this, and there's a whole family of printf commands that all use the same format strings, and they're all vulnerable if the developer forgets to put in the format string and the user can't control it. So the countermeasures, of course. Stack defenses will not stop it. We did not overflow a buffer on the stack and hit the return pointer. We just wrote directly to a RAM location, so that's not going to help. Address space layout randomization and a non-executable stack will help. The ASLR will mean that the addresses are random, so it'll be hard for me to find my shellcode. And the non-execute bit means if I inject data right on the stack like I did, I won't be able to run it directly. So that's a problem. A static code analysis tool would be a thing. Just scanning your source code for a print statement that doesn't have the format string would seem extremely easy. I think you could just use grep. GCC will warn you, but it won't stop it. Anyway, so that's the exploitation technique. So you control the right operation, and this is going to come back to us in heap overflows and other ones. So if what you have is the ability to write, this is how you take over the box with write. You find a RAM location to write to that will control execution. You write the 4 bytes to target it, insert shellcode, find the shellcode, and write that address to target the RAM. That's what we did. And so we've talked about that. All right. By the way, there are other things we could target besides C library offset table entries. We could find a saved return address. We could have put an address on the stack and just wrote to that, like the buffer overflow. We did the global offset table this time. We could hit the destructors table. When a program exits, it calls something called destructors, and you could put it there, or you could find any of the C library hooks like we did. You could hit the @exit structure. That's another structure it calls when your program ends. You could find any function pointer. And in Windows, it turns out the thing that's easy to hit is the default unhandled exception handler. You just have to find something with an address you can find and then write the address of the stuff you want to run to it. So we've done all this, I think. All right. All right. So let's try a Kahoot about that stuff, which is here. Good. All right. All right, so what does %D mean? Yep, that's just a number, a decimal number, an integer, in fact. All right, how about %N? What's that? That's writing to RAM, the crazy one. The one that just seems designed to make it easy to take over the box. I should Google someday and find out what the historical purpose of it was. It sure seems to have no intelligent purpose anymore. Anyway. All right, how about %P? It's a pointer, yep. Very much the same as %X. There is some subtle difference which I can't remember. Both of them print out the answer in hexadecimal. All right. All right, what defense will stop the format string bug? None of them. Some of them make it a little more difficult to exploit, but they don't actually stop the fundamental problem, which is that you can write to arbitrary RAM. None of these defenses prevent you from writing to arbitrary RAM, which is pretty outrageous. All right, so which one is used when a program exits? The destructors are used when it exits. C library functions are used hooks in a global offset table. All the C library functions do. And the structured exception handler is used when you have an exception like a divide by zero. But the destructors are called to clean up when you exit a program. All right, let me stop this recording.